Hey everybody. Today I'm looking at Billboard Top 100 data. This was featured in September of 2021 as part of the Tidy Tuesday Data Challenge. And if you're not familiar with that, I recommend a Google search. It will take you to a GitHub page like this, where you can find a little bit about the data set for that week, as well as all the other data challenges that have taken place as part of Tidy Tuesday. The Top 100 data actually consists of two data sets. Billboard and audio features, which I'm actually calling audio in my work. The Billboard set is going to include information about Billboard chart rankings, and audio features is going to include information about Spotify metrics on the different songs. You can see that on this GitHub page there is some code that will allow you to download the data directly, and I've basically just copied and pasted that over here. The one real difference between that code and mine is that I've called the audio features audio, just for a little bit of brevity. All right, so let's start with the Billboard data set here. Every row consists of one song for 1 week. So for instance, Don't Just Stand There in July, the week of July 17th, 1965, charted number 34, and that was by Patty Duke. The following week, it was down to 22. Now remember, lower numbers are better here. You want a number 1 hit. You don't want a number 99 or 100 hit. There's also a column here called Song ID that appears to just be pasting the song title and the artist together. I'm going to use that as a unique identifier of the song. Additionally, we have some other information here that is potentially interesting for a different analysis or a larger analysis. The one column that I really want to point out right now is peak position. So this is something that should always go down for each artist. So even though, for instance, Don't Just Stand There by Patty Duke started to drop on the charts at a certain point, where's those ranks? There we go, right here. You can see it went as far as 8 on the charts and then started to get higher again. The peak position goes down to 8 and then just sits there, right there with the peak position. Okay, later on I'm going to want to use the audio data set to get some information about these tracks themselves, what sort of characteristics they might have. And in particular, I'm going to want to try and answer this data question as best as I can. Are number 1 jams more cheerful in general than songs that are on the Billboard Top 100 that were not number 1 jams? There's a lot of different other sorts of analyses we could do in this set, even just looking at cheerfulness. I'm looking at whether a song was a number 1 jam or not, but you can also take into account things like how long something was on the charts, what sort of rankings it had other than number 1, and so on. I'm going to limit myself. Now, cheerfulness is a pretty vague word, but if we look at our data dictionary here, we have this variable valence, and this is taken, it's taken directly from the Spotify API, and valence is a term that Spotify uses to measure the musical positivity of a track, and that means happiness, cheerfulness, etc. It goes from 0 to 1, with 1 being the most cheerful. And so I'm essentially going to be looking to see whether songs that have charted at number 1 at some point in time have higher valence values or not, or at least different valence values. Okay, so let's get started. As I look at this Billboard set, the one thing that I see is that although I have peak position here, I don't have a specific variable saying whether or not it was a number 1 hit. So I'm going to want to take care of that. For instance, for this Patty Duke song, that's going to be a negative or a false for was it number 1. Additionally, I'm going to have an issue with the fact that every song is in this data set. Well, many of the songs in this data set are there more than once. So this Patty Duke song is in here like 9 or 10 times, something like that. So I'm going to have to deal with that. So let's start by taking Billboard, and sorry about that. The pipe is Control-Shift-M. I think I hit Control-Shift, comma, maybe. And I want to pipe that into a mutate. And before I do anything else, I'm going to save this. Let's save it as BB1, Billboard BB1 as in like number one jams. BB1 sounds like a Star Wars droid, I know, but I'm going to use it anyway. So the first thing I want to do is to add a column called number one. And this should be true if peak position is equal to 1. So maybe I'll put a couple of parentheses here because I want to put something logical in here and I want to make that clear. So peak position equal to 1. So either peak position will be 1 and I'll get a true, or it won't be and I'll get a false. Let's go ahead and do that. I'm not going to be done with that command just yet, but let's take a look at what I've got. Let's glimpse it. Okay, so you can see that I've got this logical vector, in particular that Patty Duke song was a false to start. But I want to point out something that bothers me as I look at this data set, and that is that weak ID, which I don't really need too much in this analysis, but weak ID is listed as a character vector, and it bothers me. I want that to be a date object, so I'm going to fix that. And I'm just going to overwrite weak ID, and I'm going to use a verb from the LubriDate package, MDY, for month, day, year. And MDY is going to take every weak ID character vector, and it's going to read it as a date with this format, month, day, year. LubriDate has similar functions for YMD, etc. And if I glimpse that, you can see that I fixed that issue. So if I wanted to do some time series stuff or sort according to dates, now I'm able to. Okay, now let's deal with the fact that songs are on here more than once. And there's lots of different ways I can deal with this. I think what I would like to do is to actually keep the row for each song ID. So song ID, again, being the song and the artist. I want to keep the song ID that has the peak position. So I think that's what I'm going to do. I can't just say weak position equals peak position because maybe the song was there more than once. Maybe it was a number one jam for multiple weeks. So I think what I'm going to do is to arrange this by the peak position and then just take the very first one. So, or arrange it by the weak position, I guess. So first let's do a group by. Let's group it by song ID so that whatever we do next will happen for each song. And let's do an arrange. Now, you have to be a little careful with this. I'll pull up the help file for arrange so you can see it. It's very specific. Unlike other dplyr verbs, arrange largely ignores grouping. So if I just give arrange a characteristic to group it by, the weak position, it's going to ignore the fact that it's grouped by song ID. So if I want it to group by song ID, I need .by_group equals true. And actually, I want to arrange it, by weak position. There we go. By group equals true. Okay. And let's take a view on BB1 so we can see that worked. All right. So now the thing at the top is B girls for one reason. And you can see, let's see, where's my weak position? Weak position starts at 54, and those numbers only get bigger. There's no chronological order to that anymore. So that's why that's happening. All right, now, while it's still grouped, I want to then filter. And so what I want to do is I want to filter out all the duplicates. And so a nice function here is the duplicated function. And the duplicated function is going to take a vector and give back a true if it's a duplicate and a false if it's not. So this exclamation point will negate that. So now it's going to give a false if it's duplicated and a true if it's not. So the trues are going to be the ones that I exactly want to keep. So it's going to only keep the first in each of these groups, basically. And let's take weak position again. And we can take a look at that. Let's make sure that this worked. I'm never overly confident in myself. I always like to make sure I got things right. Okay, so B girls. This is not what I was hoping for. So I don't want duplicated by weak position, because the weak position here, 54, 55, etc., what I really want is to take out the duplicate for the song ID. All right, so the purpose of the arrange is just to make sure that I'm keeping the highest ranking for this that the song ever had, the week where it was ranked the highest. Now I'm filtering out the duplicates. This is why I check my work, because I'm kind of stupid when I get right down to it. All right, so now it appears that that we have each song once. So for instance, B-Girls peaked at week 54. That's by Young and Restless. All right, fabulous. Let's see here. I don't need all these columns. Really, all I need is the song ID and whether it was number one or not. That's all I'm going to do. And, one last thing. I think I'll put this before the select. I want to do an ungroup. I want to make sure that going forward, there's not any hidden groupings in here that I've forgotten about. I don't want to mess with that. Typically, when I think I'm going to use a data set going forward, if I've done a group by and summarize or a grouped filter of some sort going on, I tend to ungroup it at the end. Sometimes it ends up not being, strictly speaking, necessary, but it's just a habit that I'm in that I kind of recommend to you. Okay, so now let's, I guess we can close up Billboard and we can just deal with BB1. Now that I think I have every song on here only once, I think the next thing I want to do, using song ID, is to take my audio data, which also includes song ID, and just join all these variables to get one big data set, BB1, with one row per song that also includes these Spotify metrics, including valence. So maybe I'll call this songs. And I'm going to take BB1, pipe it into a left join. So left join is going to take BB1 and mutate it using the data frame that I'm going to pass it next and the criteria that I pass it next. The term left join coming from the fact that I'm going to join to this data set that's on the left. The next argument that I need in my left join is the data set that I'm going to be using to do the mutating. And then I have to say what the key column is. And I probably could leave this out, but I'm in the habit also of always putting in my key column when I know it, or not when I know it, but as a way of guaranteeing that I'm getting the behaviors that I'm expecting. By requires quotes here, so I have to put the song ID into quotes. All right, great. So if I look at songs now, you'll see that the first two columns, once it eventually comes up, song ID and number one, are exactly like they were before. And then there's just a lot more columns on here. All of those other columns, as a matter of fact, that exist in that audio data set. Okay. Before I go on, I just want to take a second to say something about these NAs. There's a lot of NAs visible right from the start. And I spent a little time before I recorded this vid trying to figure out what was going on with these NAs. At this point, I'm fairly convinced that they're just at random, that for whatever reason, when the API was used, it did not give data on all of these songs. Or perhaps just some of these tracks aren't on, don't have metrics on Spotify for whatever reason. I looked at the NAs in this data set by date, and there doesn't seem to be a pattern there. There doesn't seem to be a pattern in the NAs between the number one jams and the non-number one jams. I looked at a few other variables as well. However, I'd feel remiss if I didn't at least be able to say how many NAs there are, like what kind of percentages of missing data we're having. And there are many, many, many ways of doing this in R. I first want to do it just for the valence column, and then I'll get the percentages of missing data for all the columns. So let's get the mean of is.na for songs $valence. So is.na of songs $valence is going to be a logical vector where it's true if it's missing and false if it's not. So when I get that average, the trues are being counted as ones, the falses are being counted as zeros. This is saying that about 17.5% of that data set are missing valence values. Let's see the missing data percentage for every column all at once. I'm going to use from the per package, I'm going to use map double. I have a whole vid on getting started with map and the per functions more generally. I'll throw a link to that up top. The map function first wants the name of the object that you're using. So in this case, it's songs. And it's going to view songs as a list. And so each column is going to be treated separately. Next, I need to say what function I want applied to each of those columns. And I want to basically do this thing right here. Do this thing right here, the mean of the isNA vector. So I need to code this as an anonymous function, sometimes called a lambda function. And so I'm saying I want a function of x that's given by mean of is.na of x. And so this map double command is going to go through each column in songs, and for that column, it's going to take the average number of NAs in that column. And the map double, the DBL is saying, well, give me back a numeric vector, a double vector. And so as you look at the percentages of missing values, you can see that predictably there are none missing for song ID. There's also none missing for number one. We have a few performers missing, which is interesting. That raises some questions. A few songs missing as well. That's also interesting. They're very small numbers. I'm not going to delve into it now. By and large, we're missing about 17.5% of the data in all of these. And if you look at the Spotify metrics, like danceability and energy, they're all exactly the same, which means apparently if we're missing danceability, we're probably missing energy exactly at the same time, and similarly for these other things. Which kind of reinforces this theory that this is these are occasions when the Spotify metrics just aren't available or aren't downloading. And again, I'm not seeing any trends in where that might be the case. Okay, so now I'm ready to actually try and answer my data question, which, if you remember, are number one jams more cheerful in general? So let's get a visualization first, and then I'll run some sort of hypothesis test to verify that. So I want ggplot. We need two G's in ggplot. And the data set is songs. On the x-axis, I'm going to put valence. On the y-axis, I'm going to put number one. So I have this categorical variable and a quantitative variable, and I'm going to do a geobox plot. Let's start with that. See how that looks. All right, let's put a theme minimal on that. And I don't know, I could touch that up a little bit if I wanted, make the labels a little nicer, add some color. I hope you'll forgive me if I don't do that right now. Let's just leave that. It does kind of look like songs that are number one jams have higher valence. That would appear to be the case. Now, I would never want to run a statistical test based on that observation from the visualization. However, I set my hypothesis before I did any of this analysis. And so it's I'm really set up to do a hypothesis test. Here I have one quantitative variable, valence, that's broken down across two different groups, true and false, regarding whether it's a number one jam or not. And so the appropriate test to do here is going to be a two-sample t-test. And you could make a case for equal variances here. I usually default towards not assuming equal variances. In practice, you don't lose a lot of power based on that assumption, and it's just safer. Also, this data set is so huge, it's not going to matter regardless. So I would like to know if valence is related to number one, and the data set should be songs. Okay. So, glancing at this, I can see a p-value of 0.01115. So that's a pretty small p-value. It's under a typical level of significance of 0.05, indicating that, in fact, valence are different between these two groups. Since, in fact, the valence is higher in the group for which it's true, the number one jams, we could also make the one-sided conclusion as well, that the valence is higher on average for songs that are number one jams. So let's make this conclusion as sort of a, let me write it down, but I want to stress I'm making sort of a preliminary conclusion. So yes, number one jams are more valent, which would typically mean more cheerful. Is valent a word? Higher valence? I'm going to leave that. Okay. However, I just want to notice right away the difference is small. So remember, valence goes from 0 to 1. Here, the two group means are 0.621 and 0.601. So the difference is about 0.02 on a 1-point scale. So that's pretty small. So how large an effect is this? What's the effect size? And I just said it in sort of absolute terms. It's about 0.02 on this 1-point scale. I'm going to compute a Cohen's d. That's one way that we can measure this. And Cohen's d is going to essentially just take that difference and then divide by a standard deviation, a sort of pooled standard deviation, to give us a sort of like a z-score that will be readily interpretable. If we get a value over about 0.5, we would normally think of that as being a notable effect. If we start getting a Cohen's d, if we get a Cohen's d that's about 0.5, we'll start noticing it as a moderate effect, a little more notable. If we get a Cohen's d that's closer to 1 or even higher than 1, then that's going to really stand out. In order to compute Cohen's d, I'm going to need the difference between these two group means, and I'm going to need their respective variances. So, or their respective standard deviations, I think is fine. So let's go ahead and get that. By the way, as we look at this plot, I'm going to be a little informal about this. As you look at this plot, the variances in the two groups, the spread in the two groups, are very, very clearly similar. I could just honestly take the variance in either one of those groups and use it as a pooled variance. I think I will actually compute it on second thought, but you really could just take the variance from either group and be just fine. Let's take the songs data set. Let's group it by number one. Let's do separate calculations for number one and non-number one. Let's do a summarize with two M's. And let's get average valence, which is going to be the mean of valence. Na.rm equals true because I have all those NAs. And then let's do a similar thing for the standard deviation of valence. And I'll do the standard deviation of valence with, again, an Na.rm equals true. And I say standard deviation. I think I want variance. I think I need variance. Okay, so there's a nice little tibble. I think I'll save it as df because I'm going to use it programmatically here in a second. You can see the variances are really, really similar. If we take the square roots, the standard deviations will be even more similar. And then, of course, you can see that difference in the averages that I just computed a second ago. Let's see here. How about a pooled standard deviation? So what I'm going to do is to take the square root of the sum of the two variances. So that will be df $var val. There's no NAs in there. And then I'll divide that by 2. Okay. So basically take the average of the two variances in there, take the square root to get a pooled standard deviation rather than a pooled variance. And now the Cohen's d is going to be the difference in those two averages. So how about df $ average valence? And then that's supposed to be divided by the pooled SD. Okay, so the thing that we're going to have here in this numerator is going to be the actual just raw difference. The thing that we have in the denominator is measuring sort of the overall spread. And so what we're going to get now is a unitless measure for sort of how different these two groups are from one another while taking into account the variability in the data. So let's actually print that out to wrap this up. There we go. So we have a Cohen's d of about 0.083. That's a very small number. You can think of this kind of like a z-score or a t-statistic. If you saw a z-score or a t-statistic of 0.08, you'd be rather dismissive of the difference between two groups, and that's what this is indicating to us here. What this is saying, by the way, is that although this difference between these two groups, number one jams and non-number one jams, is statistically significant in the sense that it of the hypothesis test, it's not an important difference. And if you were trying to make statements about number one jams versus non-number one jams, you wouldn't expect a very large effect size as you compared number one versus non-number one jams and looked at their valence levels, at their cheerfulness levels.